Organic chemistry. My name is Robert Carlson. So, this first video is just an introduction to organic chemistry and chapter 1. And they're going to be in a series here. So, we're interested in structure and bonding. We may not get to all that, so most of my videos are about 8 to 15 minutes long. So, I try to limit the time that I use, but I want to be very efficient when I'm using that time. So, organic chemistry is strictly devoted to study of carbon-based compounds. The word organic literally means derived from living organisms. And at some point in time it was thought that they were vital. So all organic compounds were vital for living organisms. Oh, then you figured it out, vitamins, and yes, you make that connection. In 1828, though, Wohler discovered that I can take ammonium, isocyanate, heat it up, and I just made urea. And urea is an organic compound. So vitalism was disproven at this point in time, that organic compounds do not have to be from living organisms. Vitalism does exist today for those who believe that into natural plant-derived vitamins and flavoring and compounds. But compounds can also be synthesized. That's a discussion for probably another day, probably a whole semester. So, some review time. Principles of the atomic structure. Atoms can be broken up into protons, electrons, and neutrons. And if we remember our periodic table, it's something like this with carbon in the middle, and it probably had like a 6 at the top, 12 at the bottom, or vice versa. Each periodic table is a little bit different. The atomic number is the number of protons. The mass number is the number of protons plus the number of neutrons. And as we remember now, we could also then have isotopes. Isotopes are compounds that have the same atomic number and different mass number. And yes, carbon has 3 isotopes. There's carbon-12. It's most abundant, like 99%. There's also carbon-13, a little less than 1%. And the remainder is carbon-14. And all these have 6 protons, 6 electrons. The difference is carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. Carbon-14 is radioactive. It has a half-life of 5,730 years, so it is radioactive. And it can be used then to determine the age of organic materials, up to roughly 50,000 years old, with pretty decent accuracy. After that, you may have to turn to potassium for isotopes, but then again, this is for living organisms. So the electrons, where we're going to be interested in organic chemistry, because you're going to hear me say electron rich or electron poor. So we need to know about the electrons. There was the Heisenberg uncertainty principle, which says basically you cannot determine the position and the velocity of the electron at the same time. Position and momentum. We'll just go velocity. If you know one, you cannot know the other. And so, review some electron densities. The electron density is the probability of finding an electron in a particular part of the orbital. So it's where we're most likely going to find the electron. And the electrons are what actually do the reactions in organic chemistry. And it relates to electron configuration. So here we have our orbitals. From the lowest energy, 1s. Next highest energy is 2s. Then we have our 2p's. And if you remember right, there was 2px, 2py, and 2pz. Then there's the 3s, 3px, 3py, 3pz. In energy, then of course it'd go up to 4s, etc. So remember that the s's can hold a maximum of 2 electrons. 2 electrons. So the p's, each one of these can hold 2 for a total of 6 electrons, etc. So the px and py and pz are known as degenerate orbitals. They are equal in energy, which means when we have our p orbitals, I'm just going to draw it representing boxes. When we went to fill these degenerate orbitals, we had to put 1 in each one before they can become spin paired. And that was known as the Hund's rule. Degenerate orbitals must be singly occupied before they can become spin paired, like I have shown here. So what is the shape of an s orbital? An s orbital is a sphere. The p orbital was our dumbbell. And in the middle where this node is, that is where the nucleus is located. And sometimes you may see it drawn in this manner, where we have a nodal plane. So this is a plane where the nucleus is right in this plane. And so we have one node coming out the right side and another node coming out to the left side to actually try to show 3D. So how would this look in an atom with just the p orbitals besides a mass? So here I have my px is the yellow. Py is the yellow. I'm trying to represent my pz. And then my orange, hopefully you can see the difference in colors, would be my pz. And all these superimpose at 90 degrees. So in the very center here of all this would be our nucleus. Hopefully you remember some of this from Chem 1. but I'm just trying to knock the rust off the old noggin. So, electron configuration. We're interested in electrons. So if we have hydrogen, hydrogen is 1s1. Helium is 1s2. Lithium is 1s2, 2s1. Beryllium 1s2, 2s2. Boron 1s2, 2s2, 2p1. Carbon 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3, until we eventually get up to neon, which is 1s2, 2s2, 2p6. Then we'll go to the 3s, etc. So hopefully you remember this. So for organic chemistry, though, we're only interested usually in the first 3 rows for electron configuration on the periodic table. Oh wow, that's kind of an ugly looking periodic table. So we're only interested in the first 3 rows, where we find things where this is the S. Yeah, I need S blocks. This is helium over here, hydrogen here, lithium, beryllium, etc. And this is the P blocks in here, which means there's only 6 of these. 1, 2, 3, 4, 5, 6. So this first one here would be, this is beryllium, this is boron, carbon, nitrogen, oxygen. Get rid of this, I got an extra row. Fluorine, neon. This row shouldn't be here. And the reason we're interested in those is because of Chopin's. Most organic compounds are going to contain carbon, of course. The next major component is hydrogen. Then they can also contain oxygen, phosphorus, nitrogen, and sulfur. Hopefully a lot of this has been review from your days in Chem 1.